All right, hi everyone. So this is lecture 6, and I'm pre-recording this because I'm going to be traveling and I will not be able to be live. So um, today we're going to continue on talking about the cryosphere. So on Tuesday, Dr. Zach Labe gave a really great presentation about the Arctic and how climate is impacting the Arctic at a disproportionate rate, right? That Arctic amplification. So I'm going to kind of go over a little bit about what he mentioned with the Arctic and sea ice, and then we'll talk a little bit about other components of our cryosphere. Okay, so we'll talk about how important sea ice is to our climate system. We'll talk about glaciers and how and why sea level is rising through time. Okay, so I'm going to start with a science experiment here. And first, I should say that today, instead of having a check-in activity after class, you're just going to submit your polling questions. It's already on there for you, so the questions are already written out, so you just have to click in as you watch, and that will count both towards a check-in grade as well as today's Zoom participation. Okay, so just be sure to check in as you're watching. All right, so I have 2 cups here, and these are representing the 2 types of ice we have on our Earth. We have land ice, which means the ice is not yet in the ocean water. It's up above, off of the ice, or excuse me, off of the water on land. So I have ice here in this little mesh colander. And you can see the level of water is denoted with a black line here in this cup. And then on the right, I have sea ice. And so the ice is already in the water. You can see the ice floating at top and the water level is shown with the black line. And so my question for you is that when I heat these systems up, the land ice and the sea ice, and I'll show you that I do this with a hair dryer. So I'm just adding heat to the system. What's going to happen when the ice melts? Which cup will have the greatest rise in water level? Will it be the land ice, the sea ice, or both will rise equally? So be sure to take a moment with all these questions. I know we're not going to have the same dynamics because this is recorded, but just really think about this. Okay, so I'll give you a second and we'll get back to it. My next experiment for today is a volumetric flask. So here I have a volumetric flask, and I'm just going to unblur my video here for a second so you can see this a bit better. So this is a volumetric flask, and what it does is it measures the volume of the liquid that's in the container. Okay, and so I have water here right now. You kind of see it here. And what we're going to do is we're going to heat up this volumetric flask by using this little mug warmer. Okay, and I haven't marked the line yet, but I will right now to denote the line, the volume of the water here. Okay, so it's right about that line, that black line. And so the question is, what's going to happen to the volume? This is measuring volume. Will the volume of my water after it's been heated stay the same, lower, or increase? Okay, so I got that set up right here. You can see it on the corner of my desk, and we will continue. Okay, so as mentioned by Dr. Labe or Zach on Tuesday, sea ice is frozen seawater and it grows during the winter months, winter season, and it melts in the summer. And it's important for many things, not just climate. It's important for humans and animals. It's a very, very, very critical kind of keystone component of many ecosystems. So we'll talk about that. So one of the main reasons why sea ice is important is this idea that it helps with the formation of deep, salty, cold water. Okay, when water freezes, when the salt water freezes, the salt is not incorporated into the ice crystals. Rather, it's ejected outward. And this pocket of extremely salty water is what we call as brine. Okay, I forgot to load this, but hopefully it works here. We can see this brine.
Over the course of about 12 hours, the super salty ice stalactite grows, trapping anything it touches in ice.
All right, so you can continue watching that on your own. It's linked in the show notes, or the show notes, in the lecture notes here. But main thing is that when salt water freezes, the salt does not freeze with it. And so you get very salty waters beneath this area. So really important for that deep water formation of our thermohaline circulation. Okay, so why is sea ice important? Well, on average, it covers about 7% of our ocean surface, and it's bright. Okay, and so that impacts our albedo, and it also limits the exchange of heat and water vapor to the atmosphere in those polar regions. Because if you have a lot of the ocean covered with ice, you're not exchanging heat, you're not exchanging moisture, and it affects the weather and climate of that region. And so we can see that if we have less sea ice, we have more evaporation, we get more thunderstorms, more weather events that aren't normal to the Arctic. As mentioned, it has a very high albedo. About 80 to 90% of incoming sunlight is reflected as compared to ocean water, which has an albedo of just about 10%. Okay, so it really, really important for global temperatures, important for the formation of that deep ocean water as part of the thermohaline circulation during that freezing and that ejection of brine, a unique habitat for polar ecosystems. And lastly, something that we may not consider, but is very important for many groups and people, is it affects navigable waters and access to natural resources. So it is potentially now easier to move products and goods because you don't have to go all the way around, maybe through the Panama Canal. You can just go up and around. But that can have consequences too. Okay, so Zach does a really great job of talking about some of these terminologies, but just to reiterate, the idea of sea ice extent is the area of seawater covered by any amount of ice. Sea ice concentration is the fraction of seawater covered by ice, and sea ice thickness is the depth between the sea surface and ice snow layers. So thickness is important too because it's one thing to have, thin ice that can melt away each season, each summer, versus very thick multi-year ice. And that's another important concept. Okay, so if we look at, for example, a satellite image that's looking down on the sea ice in the North Pole, which of the squares here would not count as sea ice cover for calculating sea ice extent? All right, so the answer here is B because we need to have more than 15% coverage, and B would not really be considered sea ice extent because there's more open ocean than there is sea ice as compared to A and C. All right, so that's how we can do this. We look at satellites, and the satellites can do some machine algorithms, some processing of the data to give us more real-time measurements. We don't have, people going out there. It's just not possible all the time. Right, so sea ice extent versus sea ice volume. So volume incorporates the thickness, right? Because volume is length times width times height, or area times height. And so, for example, if we look at the Arctic sea ice thickness and volume, we can see that just because the sea ice has the same extent as it did in 1980, for example, that doesn't mean the thickness or the volume is also the same. We have to consider what's happening beneath the surface. So that's one thing that we're not always able to look at with just satellite measurements. We have to go out and sometimes make real measurements in person with different stakes and radar measurements to be able to understand just how thick that ice is as well. So first year versus multi-year sea ice. First year sea ice is ice that formed over just one winter and then completely melts away in the summer. And they're usually pretty thin, only about 30 centimeters thick. And they are physically weaker because there is some salt. So when I say all the salt gets ejected, it's not true. There's still a little bit of salt and impurities in the ice, and that actually makes it weaker, which allows it to be broken up more readily during like a wind event or breaking waves, right? So storms. And then when you break the ice into smaller pieces, those surface areas are now smaller and can melt faster and can be impacted by other factors. And so we want more multi-year sea ice because it is stronger and it's stiffer and it's less likely to break apart, which keeps the surface area large and prevents that ice from melting. Now, one of the main issues is that our multi-year sea ice is disappearing quickly. So this is showing you some data, it's a few years old now, up until 2019, where we have many, or excuse me, much more single year ice, young ice, and very little ice that's really over 4 or 5 years old anymore. And then so that leads to many issues. Okay, so what month of the year is sea ice extent in the Arctic at a maximum? All right, so the sea ice extent in the Arctic over the North Pole is at a maximum around March. And the reason for that is that it takes time for the water to cool down, right? We talked about how water has a high specific heat capacity, and it takes a lot of energy added or removed to change its temperature. And so the sea ice will form at the end of the winter. Well, it's forming during the winter, but the maximum extent will be at the end of the winter season when the water has had all those extra cold months to really allow for that freezing. So the minimum is excuse me, the maximum is in March, and our minimum, when we see the least amount of sea ice, is usually towards the end of summer, early fall, so September time. And this is for Northern Hemisphere. You kind of get the inverse seasons in the Antarctic because of the opposite seasonal effect. Okay, and here is the Antarctic, right? So we can see that the maximum in Antarctic is around October, and the minimum in the Antarctic is around March. So again, sea ice, important for the ice albedo feedback, and we can see, and this is an image from Zach's amazing website, that our Arctic sea ice volume is quite low. And we can see that trend through time, 1980s in the dark blue, 1990s in the light blue, 2000s in the white, 2010s in the reds, and we can see that, pretty much as we move into the future and as we move forward in time, our sea ice volume is decreasing. And this is important because we need sea ice forming to help with that thermohaline circulation. Um, the Gulf Stream on the east coast of North America, or the western side of the Atlantic Basin, is pulling salty water from the tropics northward. And so it's already pretty salty, and then you allow it to freeze and get even saltier water, and it becomes super dense and sinks. And so this right now is one of our important deep water formation regions of the thermohaline circulation. And the same is true with Antarctica. Uh, the waters are cold, but pretty fresh there, because we don't get as much evaporation because it's not as hot around the Southern Ocean. But the way we get the water to be saltier, again, is through sea ice formation. So here is our thermohaline deep ocean conveyor belt. What could reduce the seawater salinity in the North Atlantic and potentially slow down the thermohaline circulation? Well, it would be adding more fresh water. Okay, so formation of sea ice would make the water saltier, more evaporation would make the water saltier, and more melting of the ice, of land ice, excuse me, like the glaciers on Greenland, would add fresh water, which would reduce the salinity and make that thermohaline circulation potentially slow down. And we are seeing that. Okay, so there's some recent studies, and I want to avoid sensationalist headlines that our thermohaline circulation is going to shut down. It's never going to probably shut down in our lifetimes, but it can slow down because if you're not forming as much deep water, you don't have that pulling of water down. It is slowing down. Okay, it doesn't mean it's going to stop. But when we compare the North Atlantic Ocean circulation today to that of, say, the last ice age, there was a difference in speed. And so there's a lot of work going into understanding this. But what we need to know for this class is the feedbacks, right? Why we need the sea ice for that thermohaline circulation. Okay, and we can think about that using a feedback system or a feedback loop, right? So when we look at our feedback loop, sometimes, I don't have the lines driven or drawn already out for you. So you have to think, where would we start a change? Are we starting the change in radiation reflected or maybe global temperature? Probably global temperature is where we're going to start. So if we increase global temperature, that will decrease the amount of sea ice because our oceans will be warmer. And so that's a negative coupling here. And if our sea ice is less, that means we have more ocean exposed. Okay, so again, a negative coupling. If there's more ocean exposed, our planetary albedo goes down. Okay, another negative coupling. If planetary albedo goes down, our radiation reflected goes down. Less is reflected, more is absorbed. So that's a positive coupling. And then if our radiation reflected is decreased, then our global temperature will increase, which that is a negative coupling. But again, when we look at what happened when we get back to the starting component of our loop, we have a plus and a plus, which means this is a positive feedback, okay? So even though there were many negative couplings in this loop, the overall change that we end up with is in the same direction or the same sign as the initial change. So that's a positive amplifying feedback, okay? So again, Zach did a great job of introducing this idea of Arctic amplification, right? Our Arctic temperatures are increasing at a much greater rate than the rest of the globe, partially and partly, well, really mainly due to the changes in albedo, which are really localized and impacting weather patterns and localized temperature. Okay, so Arctic amplification is this idea that the globe has increased by about 1 degree C, but our Arctic temperatures are increasing about 2.5 times that. So we're at 2.5 degrees C observed temperature change over the Arctic. So a huge difference. And this is likely to continue unless we curb our carbon emissions and really reduce those greenhouse gases in our atmosphere, right? So again, another great graphic from Zach showing the difference between ocean, land, and the Arctic, right? And again, the ocean is still warming, but at a slower rate because of that specific heat capacity. The land will increase faster because it can absorb heat and change temperature faster because it has a lower specific heat than water. And then the Arctic is even faster. And this is a really great graphic to demonstrate that not all the change will be equal. And that is important to consider as we move forward in time. Okay, so Zach mentioned this. We'll reiterate what is Arctic amplification. It's the fact that the Arctic is seeing more change. It is seeing an amplified change in temperature of about 2 to 3 times the rest of the global average, mainly due to the changes in albedo, which are impact albedo and moisture content. So albedo is impacting the reflectivity, which means there's more heat in this area. And also when there's less sea ice, you have more open ocean, and that open ocean allows for more heat, more moisture, which we know helps form clouds, which can form weather. And so there's a lot going on here, many positive feedback loops. And unfortunately, the Arctic is seeing this rapid change. Okay, so sea ice is important for animals, right? We've all seen the pictures of the polar bears here, but it's not just polar bears. It's other bird or other animals like seals that oftentimes use the sea ice for birthing. We also have birds that use it as a resting location. And I wasn't able to find it because I'm not sure it was ever published, but I went to a presentation or a conference once and someone showed this really cool GPS tracking. So they have certain polar bears that have GPS collars on them, and they're able to track these polar bears. And when there's, obviously less sea ice in the past few decades, these polar bears are having to swim further, exert more energy in order to find food. And so we can see just how many more calories these polar bears are having to exert just to find the same, calories of food. So it's interesting research, and maybe I'll try to find it again, but I had trouble locating that. Now, uh, sea ice is also critical for humans, right? We have many indigenous people and groups and populations that live in the Arctic that have relied on sea ice for, millennia, and they use the sea ice for hunting seals, whales, walrus, fish, crabs. And unfortunately, they can no longer rely on traditional indicators of, where the sea ice is going to be thickest or it's going to be thinnest, or, all of this traditional knowledge, because the climate is changing so quickly. And this is really disrupting these communities and their way of life and their well-being. And then, so when we think about climate change, it's not just about the planet, right? It's about people. And so we always have to remember that people are important too. Okay. And so every few years, maybe it's every year, the National Oceanic and Atmospheric Administration puts out an Arctic report card to kind of go through what is happening in the Arctic, because it is changing so much faster than the rest of the world. So we'll take a moment to listen to this, watch this video here, and we will see what is happening. And this was from 2022.
Human-caused climate change is having an ever-increasing and profound effect on the Arctic. From the ocean to the air, warming trends are continuing, and air temperatures in the Arctic are rising faster than the global average. In 2022, average annual surface air temperatures were the 6th warmest since 1900, with the 10 warmest years all occurring since 2011. Sea ice is thinning, far below conditions that existed 30 years ago, and older ice remains scarce. This loss of sea ice has enabled more shipping through the Bering Strait and Beaufort Sea, bringing with it more human-made debris, increased underwater noise, and the risk of potentially catastrophic incidents, such as oil spills. All of this activity has wide-reaching impacts on Arctic ecosystems. Seabirds are natural indicators of the health of marine ecosystems, and in 2022, Bering and Chukchi Sea communities reported the 6th consecutive year of seabird die-offs, most likely due to starvation, and coinciding with the loss of ice in those areas. Prior to 2015, seabird die-offs were rare in Alaskan waters and were usually wintertime events linked to disease outbreaks and above-average ocean temperatures. And both of those factors are projected to increase in coming years. Rainfall has also been increasing and likely transforming Arctic regions from snowfall to rainfall-dominated climates. In 2022, this was most apparent in eastern Greenland, Svalbard, and northern Norway, and in the central Arctic, with more consecutive wet days generally coinciding with reduced sea ice coverage in warmer months. Extreme weather, from heavy rainstorms to drought, has become more frequent, and the impacts of these events can be disastrous. At the peak of an unprecedented September heat wave over Greenland, more than 1/3 of the ice sheet's total surface was melting. A potentially large source of sea level rise is melt from the Greenland ice sheet. As warmer air and warmer water continue to melt the ice, impacts to ecosystems and communities within and far beyond the Arctic are already underway. The evidence is clear. Human-caused climate change is transforming the snowy and icy Arctic into a warmer, wetter environment. To limit these harmful consequences to the Arctic and beyond, it is essential for society to reduce greenhouse gases worldwide.
All right. So our Arctic report card, emphasizing what we've already said and what Zach has informed us about. All right, so how did we investigate sea ice changes in the past prior to, say, 1950, when we really started having satellite measurements? and how do we monitor sea ice today? Okay, so one way we did that is through shipping records, ocean temperature records, and we can also look at different chemicals in the ocean sediments produced by ice algae. So if there were those chemicals in the ocean sediment, in the sediment at the deep ocean, it means that there must have been sea ice in that area. So it's not a perfect, we would call that a proxy record, but it helps us understand a little bit more about that. So further back in time, shipping records are important because, if there wasn't sea ice, then the ship could go through. And if there was sea ice, the ship couldn't go through that area. And so how we monitor sea ice today, as I mentioned, is we can do direct measurements by people in buoys. We can go out and actually measure the thickness. We can also do nuclear submarines. So submarines that are underwater can help us understand some sea ice variables. And then really since the late 70s, we have satellites that monitor sea ice extent. All right, so some recent news in terms of our sea ice in the Arctic. So where is it? Here it is.
In the Arctic, including Canada's north, ice is an important part of life for polar bears and the people who call this region home. But a new study reveals the frozen sheets over these northern waters are actually disappearing faster than previously thought. And our window of time to save that summer ice has now closed.
We find that even in the emission scenario with the lowest emissions, we still see an ice-free Arctic by the middle of the century.
Since satellite records began in 1979, summer Arctic ice has already decreased dramatically from a high of more than 7 million square kilometers to just over 4 million square kilometers in 2022. Projections suggest that most of that September ice will disappear within the next few decades.
That means that you could send a ship straight over the North Pole. Open water, nothing in your way.
Future opportunities for shipping and cruise ship travel will be tempered by ecological costs. Loss of sea ice in the summer puts Canada's already vulnerable polar bear population in further jeopardy, while threatening to forever change the way of life in northern communities. There's also growing evidence that lower latitudes will see impacts too.
There is a theory that if you take away the sea ice, that changes the atmosphere over the Arctic,
which some climate experts believe could lead to a weakened polar jet stream.
So a weakening jet stream would affect weather patterns, causing slower moving systems, which could lead to flooding and more active weather. It would also allow strong areas of high pressure, like a summer heat dome and a polar vortex, to dominate for longer,
leading to even more weather emergencies. The loss of Arctic sea ice in the summer now inevitable. It's the rest of the year we can still work to protect. Heather Urix, West Global News, Calgary.
Oops.
Welcome to the News Hour.
All right, so we have already committed ourselves to so much warming, and therefore that's what that study is trying to emphasize, is that we are on our trajectory to have a sea ice-free summer, and we've committed to that because we hadn't stopped our emissions, however many years ago. Okay, so we'll continue talking about glaciers. So our next component of the cryosphere are glaciers. Okay, so what are glaciers? Glaciers are defined as a slow-moving river of ice on land. They are either located at higher elevations in our mountains, because as we move away from the Earth's surface, it gets colder, which allows those rivers of ice to exist, or they have to be in polar regions where it's generally colder, right? And so these are our main source of land ice, water that is stored on land in the form of ice. So this map shows you many of our world glaciers. So you can see the Himalayas, for example, high elevation mountain glaciers. And of course, we got Antarctica and Greenland. So a few types of glaciers. The first is the valley glacier, and these are formed in valleys in our high altitude regions. And they typically are going to end or terminate at a glacial lake. So they move or they flow down slope, and then as the temperatures warm, as you are descending in elevation, they will have a terminus that is in equilibrium with that temperature, seasonal temperatures. And so you can see there's these lakes at the bottom, whereas the water is melting or the ice is melting, you can get these little lakes. Okay, so these are in our high elevation areas. We have tidewater glacier, and these are glaciers that are valley glaciers, but they're reaching and terminating at the sea. So a really great example of this is the glaciers of Antarctica and Greenland that are near the edges. So they're terminating at the ocean. And so here is an image of this tidewater glacier coming down, and you can see it's reached the water surface and it's hanging out right there at the sea. Okay, then there's also what's known as ice caps. So these are pretty flat surfaces at high elevations. And so we get a lot of ice cap coverage, for example, in the Himalayas and in places like Svalbard and these high elevation and polar kind of latitudes. And then an ice sheet is a continental glacier. More than 50,000 square kilometers. Another way to think of an ice sheet is it's a piece of land that is covered in many, many glaciers that are all connected. Okay, so you get pretty much full coverage of your land surface with glaciers. And so today we have 2 ice sheets on Earth, Greenland, and Antarctica. So the main thing about an ice sheet is that ice sheets have many individual glaciers. And so you can see here in this study based from Eric Grignot and his group from 2011, and this is out of UC Irvine, we can see the speed of many of these glaciers, how they're moving. And so many glaciers combined, and they all are moving to lower elevation towards sea level due to the pull of gravity. So they're moving out towards the ocean. So here is an example. We have our bedrock, our ground, our snow accumulation, our ice sheet on top, and the ice is flowing slowly out towards the ocean in all directions. And so when we think about our glaciers, they are in a constant accumulation, growth, or an ablation loss. And whether or not we have addition of mass or removal of mass kind of determines whether or not the glacier is getting bigger, staying the same, getting smaller through time. So how do glaciers gain material or gain mass? They can gain more mass through snowfall, right? If it's cold enough, that snow won't melt, it'll stay around. We can get more mass through avalanches and blowing snow, right? So that snow can accumulate on to that surface. And we can gain more mass by refreezing at the base or on the surface. So oftentimes there's a lot of heat coming out of the bedrock from deeper within the earth, and that can cause the surface or the base to melt, but that can sometimes refreeze. Now, how do glaciers lose mass? Well, they can have obviously surface melting. So in the video, we said that about a third of Greenland experienced surface melting during the summer months in 2022. We can also have basal melting, which is that's what I mentioned, that melting underneath the basal melting. We can lose mass by calving icebergs. Okay, so when the water and the ice meet, now the ice is kind of floating on the water a little bit. We call that an ice shelf. And then those pieces can break off, and that's how we get icebergs. And we also have sublimation, which is going directly from solid ice to vapor. We skip that evaporation process. Okay, so as mentioned, sublimation is that ice transforming to water vapor without going through liquid stage. That's just one way it can lose mass. You can also just have melting and then evaporation, especially in Greenland. So here's an example of this surface melting. It's a significant part of the mass balance for Greenland because Greenland is quite a bit closer to the equator than Antarctica. And so Greenland is used to having these seasonal melting, but it's accelerating, right? So that's the big thing is it's accelerating. But these are what some of that ablation or loss of mass looks like on the surface of Greenland. Okay, and so basal melting, as mentioned, it occurs beneath the glacier due to the geothermal energy or warmer ocean water for those glaciers that are terminating, those tidewater glaciers at the water surface, right? So for example, this is showing you a temperature profile of the polar glacier. The glacier is quite cold in the middle. And so this is depth, right? So here's our thickness of our glacier. It's a little bit warmer at the surface because it's going to see more of that incoming sunlight that will have an impact on its temperature. And then as we get closer to that rock and that geothermal heat coming from the interior of the Earth, we will see an increase in temperature. And so our glaciers don't actually move at the same speed all the way across and within depth because of the differences in temperature. Okay, so calving is this process where the ice is separating from the glacier. It's actually an amazingly beautiful phenomenon. And if you ever get a chance to see it in real life, hopefully you can do it from a very safe distance because these termination areas of glaciers are quite large. So it's hard to put into scale. You know, some of these are several hundred feet high, right? And so when you're dumping big pieces of ice into the water, you can get kind of like miniature tsunami waves. And so if you're on a boat, it could be pretty risky. But I have a video here showing one of these really cool calving events from a Greenland, or I think it might have been an Alaskan glacier. Okay, so thinking about these mass balance processes, which of these represents an accumulation process for a glacier? Okay, so A is an avalanche, B is iceberg calving, and C is surface melt. So we know that calving and surface melt are a loss process, and so accumulation is this avalanche. So A is the answer here. Okay, so glaciers are very similar to those rivers, right? As I mentioned, they're just rivers of ice. They move slowly on the edge and they're much faster in the middle. And that's because near the edge, where the ice is scraping against the rock on the valley side, there's more friction. And it's the same thing with rivers too. When the river water is near the edges of the riverbank, there's going to be more friction and that water will move slower. The fastest flow is going to be in the middle. And so, for example, if you put some rocks in a straight line on a glacier as your marker, you come back in a few months, you'll see that those rocks are now bent with the faster flow in the middle. And then when you look at the flow within the glacier, so now I'm cutting into the glacier and looking at it like a slice of cake, you'll see that again near the bottom, where there's more friction with the bedrock, with the surface of Earth, that glacier will move slower and it moves faster towards the top. Okay, so we're going to have faster flow at the top and middle and slower flow towards the bottom and the sides. Now, when we talk about glacier mass balance, we use these terms often called advancing and retreating. So a glacier that is advancing is growing and it's moving down slope to lower elevations. A glacier that is retreating is melting and moving upslope to higher elevation. Now, glaciers have an annual cycle of advancing and retreating, right? Glaciers will advance during winter because it's colder, and so they can exist at lower elevations during the winter season, and they'll retreat back upslope during summer. Now, that is a seasonal change. When we think about glaciers on Earth for the past 100 years, do you think overall glaciers are advancing, getting bigger, or are they overall getting smaller or retreating? Right. So our glaciers, unfortunately, on our planet are retreating on average. And this is long-term change, not seasonal change, right? So we're talking over long time periods, glaciers are losing much more mass and are moving more upslope. They can only go as far up as the land itself, right? Eventually, if they move all the way upslope and there's no more land, that glacier will melt completely. And so this is Glacier National Park here in the United States. And this is showing you the total surface area from 1966 to 2015 of the glaciers in that park. And you can see a downward trend here. So if you want to go see glaciers in Glacier National Park, you got to go soon because in 20 years, there very likely won't be much glacier left to see. One of the really great ways of understanding glacial retreat is by looking at old photographs and doing these kind of time-lapse series with old and modern, taking the photograph in the same spot. So here's the Pedersen Glacier in Alaska, taken in 1917. So you can see we got icebergs floating here in the water, in the bay, and then we also have the front edge here, the end of the glacier. And if we take the photograph in the same spot, and you can see what you're using is the topography, this ridge here, it's the same exact ridge. Now our glacier in 2005 has retreated upslope more, and now the water edge is way in the background and we're covered in grass where we used to have ice. Okay, so think about that albedo change in this area. I really like this website. This is through the National Park Service, but it lets you look at many different glaciers then and now. So here is one from the Grinnell Glacier, and you can see then is what it looked like, and here's what it looks like. And now is not even now. This photo was taken in 2016. So even 7 years ago, we can see how much change there was. So you can imagine what it looks like today. Here's the Jackson Glacier in 1911 and 2009. Okay, the Blackfoot and Jackson Glacier. Again, the Boulder Glacier. Okay, and the caption says it's now even too small to be considered an active glacier. Same here with Sperry Glacier. And you can keep going if you like. So that you have that link here. Here's the Grinnell Glacier again. Pretty remarkable how much changes have happened. Okay, so overall on our planet, glaciers are retreating. There are a few that are growing or advancing. But again, when we think about long-term overall numbers, the total numbers, more glaciers on our planet are retreating than advancing, which these are a really good indicator of the climate. They're very sensitive to changes in temperature. Now, glaciers are important for humans because the melting water, right? So here is the melting fresh water coming off of those glaciers, are important for several things. First, they are important for maintaining stream flow in dry seasons to help provide water for drinking, irrigation, industry, and generating electricity in many mountainous regions. And glaciers are especially important in Asian countries around the Himalayas, for example, Pakistan, South American countries around the Andes like Bolivia. And unfortunately, the glaciers are retreating so much that that water source cannot be relied on as much anymore. Okay, so it is a freshwater source here, showing the glaciers as this fresh water source. And here's an example of the Himalayan glaciers showing you populations in each one of these regions, number of people that are relying on those glaciers, and then the runoff variability, the flow of fresh water coming off of these glaciers, how much variability there is in these glaciers due to changes in temperature and climate. And so we can see lots of people now are relying on a source of water that is just not nearly as reliable as it used to be. Okay, and because the glaciers are becoming more, I would say, unsteady and unpredictable, we can get collapses in the glaciers, which is where the glacier itself kind of rapidly collapses or melts away. And in the last few years, we've had really, really catastrophic situations where the glaciers collapse and unfortunately kill people, right? So In India, a glacier collapse kills 19. More than 200 folks were missing. In Pakistan, another issue with glaciers erupting and worsening floods. And so I have this 5-minute NPR listen here. I just want us all to listen to what is going on here, and we can follow along with the transcript of this the situation with these glaciers melting.
Support for NPR and the following message come from SAP Concur. As the CFO for Brother UK, Stuart McLean wanted to help their employees spend less time on manual expense tasks with more time for growth and big picture analysis. Click the play button below to hear Stuart's conversation with Ryan Demaray from SAP Concur as they discuss how automating expense tasks can support employees company-wide.
Extreme flooding has left roughly 1/3 of Pakistan underwater. The flooding comes after monsoon rains that are typical for the summertime broke records this year. But there's also another factor, melting glaciers and snow. Pakistan is home to the most glaciers in the world outside of the Arctic and Antarctic. Joining us now is Ulrich Kamp. He's a geographer and has studied glaciers for the better part of his career. He joins us now. Welcome.
Thank you. Thanks for having me here.
So first, help us to understand the role of glaciers in larger ecosystems around the world.
So in high alpine environments, so glaciers are the main source for fresh water. And fauna and flora depend directly on the meltwaters from glaciers, but also snow. Then, for example, you find wetlands in high altitudes that are very important as a freshwater resource for animals. These wetlands are directly fed by meltwater.
So I'm going to ask you kind of a very Glaciers 101 question, but how do glaciers melt? Can you talk a bit about what's actually happening there?
So a glacier is a larger mass of ice that is moving, along a slope. And it can be a steep slope, like in the mountains, or it could be a more gentle slope, maybe like on Greenland or in Antarctica, but it has to move. So in the high mountains, precipitation during the winter month falls then as snow and not as rain like during the summer. So that snow accumulates over the winter month, and that ice mass now increases in volume and extent, and it's getting heavier. Then it starts moving, and then it reaches in lower elevation areas. It moves down the valley where it is warmer. So in these areas where it's warmer now, the ice starts to melt. But there is also another factor, and that is sublimation. So some of the water of the ice also evaporates directly into the atmosphere.
Can you talk to me about how that is connected to the type of flooding that we're seeing in Pakistan? How is this contributing to the flooding that we're seeing there?
So Pakistan, you mentioned that already earlier, has over 7,200 glaciers. So these glaciers are sitting in the Hindu Kush Karakoram Himalaya in northern Pakistan. And, in a yearly rhythm, increase in volume during the winter month mainly, and then, lose ice mass during the snowmelt season. So the snowmelt season is a little bit ahead of the season when the summer monsoon, hits the mountains in Pakistan. So that's also important. So you have different peaks now of meltwater flow, but also then rainfall, that feeds into the river systems. And usually they are separated. So with climate change now, the monsoon, that is of course mainly responsible for the flooding, we have on top of that now accelerated glacier melt. And sometimes it could happen that the meltwater peak and the monsoon peak actually are closer together. And that's then, a particular high amount of water that goes through the entire stream system.
With what you're seeing happening with glaciers at this moment on this planet, are you alarmed?
Oh, I'm very alarmed. So we know that when we start globally that over the last 35 years there's an accelerated loss of global glacier ice. So when we compare the period from 2000 to 2004 with the period of 2015 to 2019, we have 70 billion tons of ice that melted in this period every year, more than it did in the earlier period.
Who do we expect to be most impacted by this glacier loss?
First, of course, local communities. So when we think about the entire Hindu Kush Karakoram Himalaya range, probably around 1 billion people in the area depend on the fresh water from the water towers, more or less directly. These are population in Pakistan and in India, Bhutan, Nepal, Bangladesh. So we are talking here about South Asia and Southwest Asia.
Ulrich Kamp is a professor of Earth and Environment at the University of Michigan, Dearborn.
All right. So, as mentioned, it's not just about the planet, it's about people that are relying on this resource, and this resource is becoming highly variable and unpredictable. So if you can, you don't have to do this for the class. It's not a requirement, but there is a documentary. It used to be on Netflix, but now I think it's available on demand for a few bucks. It's called Chasing Ice. It's a really, really amazing visualization of these changes to the glaciers. Okay, so one, it shows how much work goes into making some of these time-lapse images. And it's really a must-see for anybody that's interested in photography or using the power of art to communicate, science or just communicate in general. It's a really great, great documentary. I really recommend it. Again, it's not a requirement for this course, but just throwing it out there. So as I mentioned a little bit ago, we have what's known as ice shelves. Okay, so in an ice sheet, Greenland, Antarctica, those glaciers that make up the ice sheet are flowing outwards. They're flowing slowly towards the ocean, and eventually it will meet the ocean and kind of hang out on the ocean as floating ice. We call that an ice shelf. Okay, so as soon as the ice enters the ocean, it is going to contribute to sea level rise. Okay, because we're taking mass that was not in water and adding it to water. Okay, so an ice sheet, not in water, an ice shelf in water. And so how are ice sheets doing? Well, not so great. So our ice sheets are decreasing quickly. So this is showing some of the mass change in gigatons from the Greenland ice sheet, determined by looking at satellites and that help us understand this mass change. So you can see which portions of Greenland showing the biggest change in melting. But over this 20-year record, we see rapid decrease in the mass of Greenland. And we can do the same thing for Antarctica. Antarctica over the 20, or this is a little bit shorter, probably 16-year record, 18-year record, we can see a similar decrease. And the places that are warming the most are going to be up here near the Antarctic Peninsula. So the question is, do melting glaciers contribute to sea level rise? And so here again is one of our tidewater glaciers. And when the glacier is on land, that ice is not yet in the water. Once it is now in the water, floating and producing icebergs, that ice has now contributed to sea level rise. Okay, so I have this video here showing some iceberg calving, which is pretty cool. I'm just going to mute it because it's people on a boat being pretty loud. But they're here in a boat. You can start to see the front edge, the water edge here of this glacier. You can start to see it it breaking into large pieces. So this is what we would consider an ice shelf. That ice is already floating, and now it's breaking off into smaller pieces that will then eventually become icebergs and fully melt into the ocean. And so you can see when that ice falls, it creates very large waves, which personally, I'm not sure how I'd feel about being in a boat that close to the front edge of these glaciers. Okay, so you can see big, big pieces falling off. Now, and I want to emphasize that icebergs forming, this calving process, is not abnormal, right? It's part of the cycle of our water cycle, right? We're taking water that was stored on land and now it's becoming part of the ocean again. It's just the rate at which these events are happening is happening much, much faster. So here is a big old piece coming out, and this is 200 feet, right? It's really hard to envision the scale of these events, but this is a 200-foot high piece of ice that is breaking off from this ice shelf here. And again, you can see this massive amount of wave action. Yep, big old piece of ice, big old piece of iceberg now, and some pretty strong waves coming at the boat. So this is a very interesting event. This is in Alaska. So probably a pretty warm day there and lots of mass loss on this glacier. All right, so here's a little bit longer here of some big calving going on. Again, I personally wouldn't want to be this close to that situation. Look at this chunk of ice shooting up in the waves. This is amazing. Yeah, I would get out of there. It does look like they're moving. Maybe not. Yeah, that one's. Okay, we're going. All right. So that's what it's like. So what contributes to sea level rise? Well, it's going to be when you're adding mass to the system. Okay, so here's my video of the experiment, and you can watch which one rises after a few moments of heating. So this is a time lapse, so I'm using a hair dryer here just to try to melt the ice, and you can watch the water level in both cups, excuse me, over this time period. So you can see the ice is melting in the cup on the right and ice is melting on the left. But which one is increasing sea level, or the water level, is the land ice on the left, right? The ice was being added. When you add mass to the system, you will change the sea level. But when you add mass, it will increase the level. Okay, so sea ice contributors, or excuse me, sea level contributors. Sea ice does not contribute to sea level rise when it melts because the ice is already floating in the water. You're not adding or removing volume or mass. Land ice does contribute to sea level rise because ice is not yet in the water. You're taking mass, volume that was on land, and adding it to the ocean. Okay? So when you think about climate change in the cryosphere, there are many things that are changing. Our albedo of the cryosphere is changing, and the cryosphere is one of the main reasons why Earth has the albedo it does of 30%. And we're changing that. It's going to impact temperature, as you saw in your first homework. Sea level rise, glaciers, again, not sea ice. If all of Greenland were to melt, which is not happening in our lifetimes, but it's possible into the future. We'd expect about 23 feet of increase in sea level. If all of Antarctica melt, again, something not happening in our lifetimes, it would increase sea level by about 200 feet. And so here is the IPCC's projection of sea level rise over different scenarios of warming. We're pretty much committed to at least 2 to 3 feet of sea level increase by the end of this century. Okay, so we got to check in on our experiment here. So here is our experiment. Our water has been heating up, and we can see that the volume, there's the new line of water, and there was my initial line. It's kind of hard to see. There it is, maybe. The volume got bigger. Okay, the volume increased. And that's because when you heat water, it expands. And so there's actually two components to sea level rise right now. We have the addition of water from the melting land ice, and we also have the thermal expansion of our oceans. The oceans are getting warmer, and because of that, they will expand, as shown by my volumetric flask. So right now, it's about 75% is due to the addition of water from the melting land ice, and about 25% of sea level rise is due to the thermal expansion of the ocean water. Okay, so again, here's our recap of the volume in that flask. All right, so again, cryosphere is very important for our ocean circulation, which we'll talk about next week. Our oceans store a lot of carbon. And so if you slow down that formation of deep carbon, we will leave more carbon in the atmosphere, which would then accelerate global change. And of course, albedo, right? Albedo is the amount of reflected incoming sunlight. So here's a diagram that shows surface without snow or ice will absorb more heat, and then a surface with more snow and ice. So that's all I have for you. Please take the extra time today to start working on your homework number 2 so that you can come to class next week with any questions you might have. Okay? See you then.